Heavy metals can have a serious impact if released into the environment even in trace quantities. Uptake of these metals via soil crop system has been postulated as predominant pathway for human exposure to environmentally heavy metals. Uptake and accumulation of heavy metals in plants can result from soil contamination by a single or multiple number of heavy metals. In this experiment, use the spinach Brazil plant as a sample of experiment with calcium carbide and sulfur as a heavy metals. Calcium carbide absorbs moisture and produce acetylene, which a weak analog of ethylene responsible for trigger ripening process. In this experiment, it shows from the result that the effect of carbide to the cell wall of the plant. The plant leaves slowly fall apart from the tree and the leaf turn yellow in color. It shows that the effect of this heavy metal affect to the plant very seriously. From the chemical equation, CaO plus 3C is produced Ca, C2 and CO. So the CaC2 content of the product is assayed by measuring the amount of acetylene produced on the hydrolysis. Impurities present in the carbide include phosphide, which produces phosphine when hydrolyzed with heavy metal like arsenic. The component of the cell wall affect due to heavy metals are cell wall polysaccharides, cellulose, hemicellulose, pectin, lignin, and other cell wall related to proteins. Plants have different mechanisms to fight stress, and they are responsible to maintain homeostasis of essential metals required by plants. These mechanisms are also focused on prevention of plants exposure to heavy metals present in the soil or providing tolerance to the plant by detoxifying the metals. Other mechanisms are specific and are attenuated when the respective stress is encountered. The first line of defense provided by a plant is to reduce the uptake of metals when stimulated with toxicity of heavy metals, and included the help offered by cellular and root ascoids that restricts metals from entering the cells. Many plants have exclusive mechanisms for individual metal ions and are involved in sequestering these ions in compartment, avoiding their exposure to sensitive component of cells. As a second line of defense, other mechanisms for detoxification of these metals are introduced that select, transport, sequester, and detoxifies these metal ion in the plant's local. During the time of metal toxicity, oxidative stress is pronounced in the cells and production of stress-related proteins and hormones. Antioxidant and signaling molecules including heat shock proteins synthesis is initiated.
This figure shows how the cell wall can act as a barrier against cadmium pollution. Plant cells can counteract the toxicity of cadmium in several ways, and the cell wall actively participates to most of these mechanisms. Apart from mechanisms of sequestration based on the activity of vacuoles and phytochelatins, additional decontaminating activities can be exerted by the cell wall. For example, specific polysaccharides of the cell wall and bind cadmium through sulfated moieties. Cadmium might also be sequestered in the cell wall by the activity of either cell wall-associated proteins or cell wall phosphate. An additional barrier might be represented by secondary modifications of the cell wall, such as lignin deposition. Such secondary modifications might render cell wall less permeable to cadmium, thus limiting its entry in the cell. Lignin can also bind cadmium, thereby inhibiting its diffusion into the cells. High abundance of lignin in secondary cell walls might thus make plants more tolerant to the effects of cadmium treatment.
Applications of bioremediation. Bioremediation cleaning up soil sites contaminated with heavy metal by using living organisms to degrade hazardous materials into less toxic substances. There are two types of bioremediation. First is bioreduction. Bioreduction is the non-metabolic, passive process for metal removal by plant and pet biomass. Second is bioaccumulation. Bioaccumulation is an active process to remove heavy metals from the soil only by giving